This is a video about navigation and changing parameters within SimSmith. In order to build a circuit, you need to be able to put the components into the circuit in an order that you wish, and you need to be able to set their values. SimSmith allows components to be put into the circuit with a few restrictions. One is the circuit must always start with a generator on the right side. It always will have a load on the left side, and the components will be put in between between the generator and the load. If you haven't already done it, I would encourage you to upload version 14.11, which was released today, for the simple reason that 14.11 is a version which now looks different than some of the previous versions, and that'll become apparent as soon as I add a component. I add a component by going down here, clicking on it with a mouse, and dragging it up. Notice right now it says C1. The components now are reference designators that are a little more similar to what we're familiar with in a schematic. Before they were labeled A, B, C, D, E, F, G, etc. And now they're labeled C1, C2, C3. Inductors are L's, of course. Resistors are R's. Transmission lines are T. And these are now editable. So if I want to go back to where it used to be, it's an A. If I want it to be, if I want to match some circuit that someone's printed and it's C11, I can make it C11. And it's a parameter field, just like other parameter fields, in that I can change the data in that field. So if we take a component that's in the chart already here, and we right-click on it, we see that we're greeted with a bunch of different choices. We don't have to do these things here because we can do Control D, Control C, Control V, Control X, Control R. Most of these should be self-explanatory, but R is kind of interesting. We rotate the component, but now we rotate it through 4 different variations. And we also have color. If we want to change the color for some reason, SimSmith uses 6 different colors. If there's 2 particular things in a circuit that you want to emphasize and they both happen to be green, you can come down here, click color, and change it to orange and say, okay, now it's an orange component. It'll plot orange, as you see over here. That's not in this new version, but that happened, I don't know, maybe there's version 12 or 13. So if we were to go and set the, I'm going to hold Control key down, I'm going to delete the component for a moment. If we were to come over here and set the load impedance to be 25 and this plus J25, we get a point up here. If we notice this point, and there's nothing special about this point, but it just happens to be with the way the curves are drawn on this particular Smith chart, it's at the confluence of a lot of different arcs here. The Smith chart has been called like the chart of circles and things like that at various times because every one of these lines on here is either part of a circle of some radius. I mean, you can think of the 2 vertical and horizontal lines as the radius of infinity, but all the rest are parts of circles of radii that are less than infinity. And while it's not shown on here, there's a whole bunch of radial circles, and they represent constant SWRs. There's one shown right now, which is 2. If I want that to be 3, I can just enter a new value in there, and that's a 3-to-1 SWR. So when the Smith chart was, I don't know if it's called invented or derived or whatever, it was a way for people who didn't have the means computers weren't available then. They hadn't been invented, and the only thing you were capable of doing was do the math by hand. It was incredibly tedious. The Smith chart gave you an opportunity to graphically represent a circuit, not with super precise accuracy, but with tolerable accuracy, in a way that was quick and easy to do. And if we go look at this point, there are, well, let me change SWR for a moment here. That impedance, 25 plus J25, turns out to be 2.618 SWR. If we zoom in on this point right here, we will see there are 10 arcs that intersect this point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, it's 5 arcs that come in and then leave. So if we were to take a component like a series capacitor, put it on here, we see that the impedance due to this component follows this arc. Now, if we're going to rotate this component by just hitting control, we're going to we're going to be up here with our mouse. We're going to do Control R. So we go from a series capacitor to a shunt inductor. It again is on one of these paths. We're going to go and do it again. Series inductor, one more time, shunt capacitor. 4 of the 10 arcs were used by rotating this component. Notice the reference designator did not change. If you really want to change it because you've ended up with this being an inductor, all you do is, L6, whatever. So that was 4 of the 10 possible paths you could take leaving that point. Let's remove this part, Control, left click, and let's add a resistor. A resistor here can be a series resistor. It follows this arc. A parallel resistor follows this arc. A parallel resistance of negative value follows that arc. And a series resistor of negative value follows this arc. These lines are outside the Smith chart. The Smith chart is inside the Smith chart. Are all impedances possible with a real part greater than or equal to 0. So from 0 to infinity, plus or minus, j minus infinity to plus infinity, all are mapped in this area. If r is negative, the real part is negative, you're outside here somewhere. And there's no reason you can't be outside. You generally are not outside in a passive circuit, or I don't think you can be outside in a passive circuit, but in an active circuit like an oscillator, you can easily be outside. That wasn't the point of this. The point was I used 4 more of the paths now. There's only 2 paths left. Let's add a transmission line and make it 0 loss. It follows one path on one of the paths here. If we make it a negative length, which is perfectly allowable, it follows the other path. All 10 of these possible paths were used by the addition of relatively simple components that would be incredibly difficult to do manually. The math would be incredibly difficult to do manually. So if you buy Smith chart paper, you'll find that it's got lots more arcs on it than what's shown here. And if these are shown just for convenience reasons, because you're not graphing manually. SimSmith is doing the graphing for you on its own, and the graphing that it's doing on its own, it's doing without needing these arcs. It does it in matrix equations. So, nevertheless, this is the visibility of this is done for convenience, not for need, and you don't need to know any more than that. One thing that's interesting about the Smith chart is it is not linear. The values near the center are much more expanded than the values out here. If we look at this, we go from 25 to 100, so 25 to 100 here. 2 times this much, 2 times this much this way. Here's 5 times, and if we go out here, it's 10 times, and this is 1,000,000 times here if we wanted to go out right to the edge, basically. So what we see is we see a lot more granularity in close. Well, if it's a 50 ohm system, we expect to have more of the action towards the center. So that's good. So let's look at this piece of transmission line we've got. And let's say we don't want 45 degrees. What can we do about that? Well, there's a whole lot of ways we can change this length. We can right click on the end of this and drag it. That changes the length. We can put our cursor in here. It lights up the field in blue, telling us that it's been selected. We can enter a value in there. Once we enter a value at all, any digits at all, it turns red or pink, telling us that it's edited. It has not been taken. This did not move. If we want to get this value to be accepted, we have to enter we have to press either the enter key or we have to just click somewhere else. I'm going to just click somewhere else. And now we see that it's been taken and it's good to go. There are parameters up here in here that we can't adjust by dragging. This dragging component on the piece of transmission line only affects the length. We cannot affect the velocity factor. We cannot affect the impedance. Those are values you have to enter either by putting a value in there. I just typed it and say yeah and click outside, or by being in the field here and doing things like these arrows were one of the early mechanisms SimSmith had other than keyboard entry to adjust components. This is plus 10%, minus 10%, plus 1, minus 1, plus a tenth, minus a tenth. I don't know when it was, but maybe a couple years ago, the arrow keys on the keyboard were added. The arrow keys on the keyboard work in conjunction with the preferences menu to these numbers right here are the change amounts. If you hold the shift key down, you hold no key down, the control key down, and shift and control both. So the way I've got it set up is if nothing's held down, I get a 10% change. If the shift key is held down, I get a 1% change. The control key down, I get a 1/10 of a percent change. And shift and control both, I get a 100th of a percent change. SimSmith comes with this being 0.1 and this being 0.01, but you can change it at will. You do not have to make them decade-oriented. You can do them by factors of 2. You can do them anything you want to do them. It doesn't matter. But that's what rules the effect of the arrow keys. So I'm going to hit the arrow key right now. Well, I have to get something selected here. I'm going to hit the arrow key, and we can see that the transmission line length is changing. If I hit the arrow key, but I hold the shift key down, notice it changes a smaller amount. I'm going to hold the control key down now. It's barely moving, and you wouldn't be able to see shift and control unless I zoomed in. So fundamentally, this is a pretty easy way to do it. However, as all things, you make an improvement, and you want a little bit more. Somewhere, and I don't remember again which version, but it's been maybe a year or so at least, the wheel tune direction was allowed. And none is how SimSmith generally comes. However, with nothing selected, I can still use the wheel on a mouse to zoom in and out on the Smith chart and the square chart. But if I pick either a +1 or a -1, that determines which direction does what. I can then go and just put my mouse in a field here and then roll the key. And by rolling the mouse wheel with nothing selected, with shift selected, with control selected, it's a much, well, in my opinion, that's the easiest way to do it. If you've got a wheel with a mouse with the scroll wheel. All of them are perfectly valid. There's no reason one of them is better than the other. They all work equally the same. Now, we have another couple ways to change components. Control key, left click, get rid of the component. If I bring a resistor in here, it has got a place to have a file attached to it. If I have a component that I've measured or obtained the impedance plot of it versus frequency, I can enter it here. And here's a ferrite bead. This ferrite bead, it's easier to see the impedance of the ferrite bead if I start with 0 ohms here. So there's the impedance of the ferrite bead with frequency. And let's make that go from 1. I think I scanned this ferrite bead to 180 megahertz. And we'll see that in a minute. What we're seeing right now is the arc due to this ferrite bead at frequency of 10 megahertz. That is not the impedance of the ferrite bead. That's the net effect of the total impedance of the ferrite bead, which if I click on it right here at 10 megahertz, I see it's 23.8 plus J110. If I want to see the effect of the ferrite bead at frequencies, I need to do something called sweep. And I would need a few more points than we have here, so let's put 1,000 points in there. And there's the impedance of my ferrite bead. It's incredibly nonlinear with frequency. It actually becomes resonant somewhere around 105 megahertz. It's got a little dip in it down here. Ferrite beads are notoriously nonlinear. Now, I said in an earlier video that the components had to be linear time invariant. Well, the ferrite bead we're going to call linear, but it's linear at a frequency. As we vary frequency, every time we vary frequency, it's a new problem. So being a new problem means it can still be linear. It has a value at 10 megahertz of this value. Yeah, I didn't quite get 10 megahertz there, but it has a value at 15.51 megahertz of that value. And by the time you get up here, it's got a value. This is what's known as a 600 ohm bead. What it has is approximately 600 ohms of impedance at 100 megahertz is the way it's spec'd. Similar to I'm going to delete this component now too. similar to the component, we have ability to put a file here for the load impedance. The classic thing you put in here is an antenna file. You put an antenna file in here, and you put it in there for a very simple reason. Again, I get an error here. This error will occur very, very often when you bring a file in. And what it's telling you is, if you can read that or not, it's saying that the file I brought in only had data from range 3 to 30 megahertz, and it doesn't cover frequency 1. Well, that 1's where we started. So if I make this go from 3 to 30, or anything within that range, it's perfectly happy. But it's not happy when it's outside of that. This is the classic plot of a flat dipole, where this is the half-wave resonant point, and then these points are the 3 halves, the 5 halves, and the 7 halves resonant points. A dipole is a classic nonlinear component, or an antenna is a classic nonlinear component. If you take a regular Smith chart program that does not allow this, and you've got an impedance for your antenna, say at 14.1 megahertz, that impedance won't be the same at 14.2 megahertz. So while you may analyze the effect of a matching network, it's nice to measure the effect of the matching network with the right antennas, with the right impedance for the antenna. So we've now kind of moved our way over to here. In the process of being here, we notice there are 3 ways to look at the Smith chart. One is the path. The path is a very simple way. There's nothing to be done here. This is the impedance point of the antenna at that frequency. So if I want to see something that's a little bit nicer, let's go to, say, 3 megahertz. Sorry, let's go to something like 3.8 megahertz. We're down here. If we wanted to match this antenna with an L network, I put this capacitor in wrong. And this is why it's so nice and easy just to be able to rotate it now. And that's what I really wanted to do, say. I can drag it now up to where I want to be, and I can put another component that moves me down here. Well, that will be, we're up here, we're inductive. It needs to be capacitive. It would be a series capacitor that would move me down, and there I am, pretty close to being matched. Now, when I want to sweep this from, let's see what kind of match I would get from, say, 3.6 to 4 megahertz, I would go to the sweep mode, and we only want to look at this traces the load. Let's look at just what you see at the generator. This is the effect of this network, which doesn't change value, but this is changing. And that's really, really powerful, because that's exactly what you have when you build something. So if we were concerned about a 2-to-1 SWR circle, we could say that this point on the circle is 3.74 megahertz to 3.867. So we have 120 kilohertz of 2-to-1 SWR bandwidth with that antenna in this matching network. That's kind of the gist of how to navigate around in SimSmith. One thing other to mention here is this little squiggly thing here. It's the file chooser. It came up a couple times before. If you ever get the file chooser to come up and it won't go away, you've accidentally clicked that little button. That little button says to make this thing sticky if possible, and it'll try to stay around. Otherwise, it goes away as soon as you use it. And that's kind of personal preference. But the file chooser is where you can go and find files. It's also where you can take a component that you've built and save it. There's a component I built, and that component's an in block. It can be brought into the circuit at any time you want and use it over and over and over again. These components down here are certainly not considered to be beginner part of SimSmith, but they allow you to do a lot more let SimSmith have a lot more flexibility than you could ever have without them. The ruse block is kind of interesting. It's the last component added that was like this, but it allows me to put. I can put a resistor in a circuit. I can put a capacitor in it. Now you get errors when you're messing around, so you just basically make this be small and don't ignore them for a while. And I can put and I can build this circuit any way I want, and SimSmith is perfectly happy with analyzing it. I'm not going to continue to build it, but you just build it up as you want, and you give these components the values you want, and it increases the power of SimSmith just incredibly. So anyways, the next video I'm going to do is going to be aimed at looking at voltages and currents on components. We didn't talk about that tonight, but these fields up here basically turn SimSmith into like a multimeter. And you can, like an RF multimeter, that you can look at the components, the voltages, the power, the currents in any of the components you have here. And that's something I've never seen that in a Smith chart program ever. Thank you very much. Hope you enjoyed the video. And if you, if you want to see future videos I do, you're welcome to come back anytime you'd like to the channel. Also, if you want to, you can subscribe and you can get a email whenever I post something new. I have, I think, 10 or 11 videos plotted out right now to do in this series of SimSmith basic videos. Thank you very much.